Okay. Yeah. Well, I hope it is.
Yeah, I was just thinking, please.
Okay. Okay. Let me see if this is fluids, right? Mm-hmm. Okay. All right, there we are. Okay, we're going. Now I got to get logged in here. Come on, come on. Oh, geez, it's hard to do the mouse with that. Here we go. Come on. Okay, that's this keyboard. Did we do it? I got in. Next, I got to get this thing started. Now, I don't have it up there, do I? Hang on. What are all these other things do? That doesn't do anything. And then the projector thing. Oh, I got to turn it on. What is the reflection here? Oh, it's from that light right there. There we go. Yeah, that's... Sorry about that. That's not good. But... Oh, geez. I gotta get that other piece of machinery working. Why is it flashing? It is up there, isn't it? It's up there. Is it up there upside down? It is, isn't it?
I think I'm just going to tune in this course.
What do you do? Wait a minute. Did I do this on the last time I was in here? How do I flip the thing?
Like mine so far.
Okay. Oh, here we go. Wait. That's right side up, isn't it? Is that right side up?
Yeah.
All right. Finally. You know what? Since I am here and in the, I'm going to go straight and do the word of the day to start with. Okay, so if I go down here, I don't need that keyboard. Wait a minute, why is mine not working? I don't have it on. Okay, let's use the word line. There we go. And there's the word of the day. Then let's head off, get rid of all this stuff. And is that the last page? It is. So if you don't mind, I'm going to do a copy. I'm going to paste. I'm going to paste. I'm just going to paste a few pages for. And there we go. So then go over to the book. The book sits right there. And I already did that. So let's go down and dig out a problem. Like we are digging a problem. Or I can make one up. Yeah, I'll just make one up. Well, let me just see if there's a nice one down there. There's got to be a good one down there somewhere. Okay, so there's the manometers. We'll do some of those, but I'm in the other topic right now, which is the gates. There's a gate. I think this is one of the homework problems anyway. So I'm just going to do that one. So the number it says is 261. I see part of it down here. So what I'll do, I'll grab the problem or the picture, and I'll drop it over here. Hello. There. So, and you know what I'm going to do? I'm going to drop another version of the picture over here. Can I move it out of there? Oh, it wants to. Okay, I need to separate myself, then do it. Okay. So I'll use the other one as a reference too. Okay. I'm going to have to go back and find out what he was asking for. He's obviously interested in the, I'm pretty sure, in the tension of the cable. But he does say it's a homogeneous 4 foot by 8 foot. So think of it as a piece of plywood. And I'm pretty sure whatever the weight against that thing, it's not going to be able to hold it. So it's a metal plywood. It weighs 800 pounds, which if it's a metal piece of plywood, that would kind of make sense. And it has a horizontal cable. And the water acts on the gate, which is hinged at point A, which it says in the friction. Determine the tension of the cable. Okay. So, let's start by doing, I don't know that I can do, okay, there is this thing called snippet, and snippet, I think, will not carry, from my understanding, it doesn't carry the extra baggage. Oh no. Let me try that again. Okay, where did it go? Is it still there? I'm going to do freeform select. Now, yeah, see, it doesn't carry the extra baggage. Where did it go? It dropped it down here. Here. So I'm going to go over here, and I'm going to make it into a free body diagram if I can get my drawing up far enough. Is the thing refocusing all the time? Changing the focus? Okay, so get away. Okay. So what happens is, at this particular point, your pressure is 0 because it's kind of touching the air and it's touching the water. So what happens is you get a uniform growth of pressure till you get down to here. Well, that's okay. And the key is, and I'm going to get this information from the other picture, you also have a tension of that rope. You also have the hinge force. It's going to probably look like this. I'll call it HX for hinge X and HY. I don't know the depth here, but I can look at the other picture, I think, to figure that out. Oh, well, I'm going to have to figure it out this way. Here's what I got. We got a triangle. It looks like so, and it's 60 degrees. And therefore, if I look at this, okay, I gotta keep hitting the escape key. This is 6 foot, and that's being 60, and that's 90 because I hope I drew it well enough so it looks like it's 90. So that means whatever this is, which I'm gonna call H because it's, or should I call it date? Because actually, they list it like that in the text. So I'll use the H because that's kind of what they, although, you know, I didn't think about that until just then. Maybe that should be called D as a symbol for depth, but that's okay. I mean, it really doesn't matter. So sine of 60 degrees is 6 H's, or 6 over H. So H is equal to 6 divided by sine of 60. Wrong thing. There's octaves. Let me get these back in sequence. So I can keep going back and forth that way. So clear CLC and 6 divided by sine degrees of 60 gets you back to 6.9282. 6.9282. So that's how deep this is. Now what that means that the pressure at this lower spot is equal to gamma, and I'm assuming this is water. So I'm just going to take gamma to be 62.4. It might be different because if it's moving to like 90-degree water, it's different. But I'm just going to take this, that's pounds per cubic foot. So 62.4 pounds per cubic foot times the height of, I've already forgot now, 6.9282 feet deep. And that would give me that times 62.4 gives me 432.32. 432.32 pounds, pounds per square foot. But at the top, it's 0. So in effect, let's see if I can do this again. Sometimes you can do this pretty easy. Okay, I can do a copy and then a paste. And then I'll put that where? Oh no. It's putting it inside the same selection here. Copy, do a copy, get outside the selection, then do a paste, then I can move it around. Notice it covers the stuff that's out there. That's kind of interesting. So, equivalent diagram would look like a tension and then a single force that this time, since this thing is, okay, go down. This thing is 6 feet, 1/3 from the bottom for that load would be 6 over 3 or 2 feet, because you'd have 2 feet, 2 feet, 2 feet go together. So this will be 2 feet, 2 feet, 432.32 pounds, 32.32. Then you still got your hinge X and Y, but now I can sum the moments about the hinge. You got to be careful here. Okay, so what you got, and let's see, we'll do it that way. So the 432 times 2 foot, and then minus, because this one is going the other way around, so this one's going this way around point O, or the hinge, and the other one's going the other way. So the question is, what's the distance from here to here? Well, the distance from here to here is 8, so if I remember right, yeah. So now you're looking at this, so you're like, I got to know a different number now. And this time, if I want to, I can just drag this down here. The equation looks exactly the same. Everything looks exactly the same. That triangle is the same as that triangle. The difference being that the number this time is 8 instead of 6, and 8 instead here, and 8 instead here. And then you go in here. Okay, 8 divided by sine degree of, what was it, 60? 60 gives you, where'd it go? Oh, 9.2376. So the H for the 8, yes, that's for the 6. Height here becomes 9.2376, and that's in feet. So that's the moment arm that needs to go right here, 9.2376. And from that, you can get your tension to equal 432. Oh, I have made a grotesque error. You know what my error is? Very grotesque error. I'm putting this in as the pressure, when in fact I should have multiplied it times the area of the piece of plywood and put it in as the force. So that's the pressure. The force is 4/8, which is his piece of plywood, or 32, times the 432.32. And so let me fix that mistake. Look at that. Wait a minute. Okay. Times a 4/8. 13, that sounds about right. 13,834. When I say about right, these numbers are usually pretty big. So, 13, 1, 3. Did I read that right? 13,832. No, 34. Okay, fix this. 15,834 in dots. And so, let's see. So I take that, find the tension, 2 times, twice that, because there's a moment on. 13,834, and divide that by the moment arm of the other. And actually, inside MATLAB, I should be able to carry all of that. Let me do this as a, let's see, what do I want to call this? F. I'll go back and call the other one R. So carry all the digits there. So I got 2 times F divided by R. 2995 and some change. Uh-oh. So that one was fairly reasonable. I guess trying to trick you with the drawing. You could do it the other way with the F is equal to gamma H bar A, and then the delta of I bar XX over Y bar area to find that. But you would find that in a case like this, it produces, when you work on this one and you do it this way, you question why you did it that way, because this one has less computational procedures in it. So let me see if I can find something else that looks, I guess this is a gate. We could do this one or this one. The others look, now that looks interesting. Some of them look kind of boring, some of them don't. Oh, that's an interesting one. That's interesting too. Well, I guess they all are somewhat interesting. That's funny. I thought that one was way back in there. These are all curved gates, which I haven't done yet, but I don't know. I don't know which one's most interesting. I guess I'll do this one because I have no idea why. But let me read the problem first. Oh, God. That's too many words. Let's do this one. Okay, so you got a gate. It has a cross section. Well, wait. That's that one. Okay, wait. Figure 268. But this is, oh, here we go. Okay. The gate has a cross section shown in 2ch. Closes on a open 5 foot wide and 4 foot high. So that means it's 5 foot into the page. So if this were a perspective view, it would do like this and come down, close off there, and it would be like that, and then you'd have this gate. This doesn't look quite right, but oh well, this is life. So this thing is 5 foot into the page. The gate weighs 500 pounds, and its center of gravity is 1 to the left of AC and 2 above. Determine the horizontal reaction that is developed on the gate at point C. Where's, oh, there's C right there. So now that we know it's 5 foot in there, I can just copy the picture off of that. So, let's see, whoa, wrong button. Wait, what happened? Okay. Oh, okay. That's okay. All right. Take a minute. I wonder if I should leave oh, I do have a button up there for the snippet. No, that's not what I thought. Okay, that's it. Okay. But the problem is I have it in a free form, so I need to go back to a rectangular and then do a new and just grab this. Go back to the page. And you know what? I'm too lazy to open a new page, so I'm going to drop it usually the top left corner is where it shows up. Oh, go away. Okay. So, you know what I'm going to do? Now I'm going to clip off the clip. I think I did that a minute ago, didn't I? Okay, so now I'm going to clip off the clip, but this time I'm going to do a free form. I'm going to say new, and here's what I'm going to do. Oh, come on. Oh, shoot. Okay, new again. Let's see how that does. Alright, that's good enough. Go over here. Drop it right there. Okay, so if I look at the pressure profile, I actually have a pressure already here on A from this height down. So whatever that height is, the pressure at A, is going to be gamma times whatever that height is. Then, as I go deeper, it's going to grow because its pressure is increasing. So you get this linearly increasing, and then whatever that pressure is there, it's going to be the same pressure here. I think that's about the same length of vector, and it's going to look uniformly like that. So for me, what I'm going to do now, I'm also going to have, and I didn't clip that very well, but I think what he's wanting to have is what he wants you to know, or what he wants you to answer is what's that. So luckily, pressure at this level is still water. So pressure at that level is 8 foot times 62.4, or let's see, 8 times 62.4, or 499.2. 499.2, close enough. Pressure at this level, that's 8, 9, 10, 11, 12, so that's the pressure, is equal to, this is going to sound weird, but it's 8, okay, so it is true that it's 12 times 62.4, but it's also true that it's 8 times 62.4 plus 4 62.4. Because that, you know, the 8 and the 4 go together. And the reason I'm writing it separately is, in a minute it'll make sense. So the pressure is equal to 499.2. And then 4 times 62.4. 249.6 plus 249.6. So I can add them together, but, you know, I'm going to take them right back apart. Oh, wait. I'm hitting the wrong button. Wait. Escape. Okay. I was supposed to hit this one and then do, I guess I could do it one of two ways. It's been sliding. Oh, it's still in view. 499 plus 500, and then that's about 750 or so, roughly. But the reason I broke it into these two chunks is on the drawing over here. Okay, we've determined that's 499. I don't want any more decimal spots, so I'm just going to throw that in the trash can. And then I'm going to say, my drawing is awful. I'm going to say this is still 499, and the other one was, you know what? And I'm going to make that 250. So that's a pressure increase of 250. If that's 499, then guess what? So is that. So if I want to take this thing, copy it again, copy it, but this time I'll go somewhere over in here and paste it. And then I'll find out what that blue line is, or here. I'll get rid of all that. Here's what I'll do. I'll get rid of all that. Oh, come on, here. Delete you, and we'll delete that. And we'll put a big green line across here. Separate these. That way I can start getting back in and work on this a little bit. So you look at this thing, get it up here. Oh, I think it doesn't behave. So, what are my forces? I've got one. Oh, look at this. Come on. Okay. I've got one right in the center. That happens to be 499 times however wide that thing is, times 5. And I don't remember how, oh, it's 3 foot. The thing is 3 foot wide. So it's 3 foot wide, but the thing is 5 foot in the page. Did he say that? I think he said that. Yeah, it's 5 foot wide and 4 foot high. Now here's what's so strange is this is a 3, 4, 5. So this is 5 too. So I could see where somebody might get confused as to which one to make into the page. But it does say 4 foot high, indicating that high, this is high, that's low. Maybe. I don't know. So that's the force there. Then you have a uniform force, or a component of a uniform force that originates from that pressure, which is 499. Now, like we were saying before, this is a 3, 4, 5, so this is 5, this is 3, and that's 4. Although I don't need that 4, because that 4, there's nothing in this space that's touching the water. But this is 5. That's the area there. But it's also 5 into the thing. So that'd be a 5 by 5. Did I figure this number out? No, I didn't. So I'm going to leave them without being figured yet. And then I get 1. Okay, so since this is 5, this distance, so this is 5 feet from here to here, the location of this load from the hinge is 2.5. Since that comes from the uniform load, now this one comes from the triangular, the upper part of the triangular. So if you look at it, this is the upper part of the triangular load. And so it's going to have a slightly different value in that it's going to have a triangle. It's 250 on the end. Hang on. Okay, 250 on the end. Then, if you want to multiply it, it's a times a 5 by 5. So, in other words, let's make a comparative. 499 pounds per foot squared, uniformly distributed over a 5, or just say 25 foot squared. Okay, now I've got 250 pounds foot squared. It's also distributed over the same 25 feet squared. The difference is half of the load is missing. So that half is missing. And so now that it's missing, you can take half of it off. Turns out that the centroid of this crazy little thing sits here a third of the distance over, but it happens to be 5, so it's 5/3 from here, or 5 times 2/3 from there. Myself, I'd rather have it from here, and that distance is 5 times 2/3, or 10/3. So now I've got everything I need to know, and I also could have, should have, and probably should go back and put, here, let me do this. Just say 2.5. I'll put a hinge X force and a hinge Y. It's not a big deal because I'm going to sum the moments about the hinge, and I can pick this arbitrarily. Usually I kind of like to pick it that way because X and Y, if you rotate that way, the thumb comes at you and it's a positive as far as a cross product. Uh-oh. Is it bouncing in out of focus? Oh, it's not? It's weird because the last class period it was. Okay, so I end up doing that. Now, all I got to do is track down everything. So I track down. I don't know if I want to number them as a sequence or whatever, but I know I'll color code them. Here, I can color code them off of this. Here, a gray. The gray will be this one. Here's the gray force. Then whatever that is will be this one. And then I'll go back to the original for the other one. So the gray, I think it was this one. So the gray one was 499 and 25. I got that from right here. I didn't multiply it out, so I didn't do that yet. Moment arm is this. Oh no! Oh, sorry. Moment arm is that one. That's 25. I'm sorry, 2.5. Now the question is it going the positive and negative? It's actually going this way, and that's the same way as that. So it's positive. And since I want to keep this in view, I'm just going to write the next one below it. Okay, the next one was this purple one, wasn't it? Isn't it that color? Yeah, we'll make it that color now. Here, we're there. So I'm going to have to change the other one to a different color too. Now, moment arm first. Okay, force, moment arm. This going in the same direction as the other. So first, let's do the moment arm. That's just 10/3. There's your moment arm. Now I need to slide over it. And I need 250, 25, 2. 250, 25, and it's half of that. And okay, shrink. Maybe some of my fingers may be drier than others, why it doesn't respond to me. I'm just looking at it. See, it says it's charging. Oh, I see. Okay. The little bar grows like that when it's charging. It's 99. I thought it was about to run out of battery. Okay. Now we're off to the next color. What color do I want? There, that's a happy color, I guess, especially if you're an orange. Oh, that's weird. So you got this one. Now this time it's going this way around here, or minus 499, 3x5. And what is his moment arm there? I think that bottom was 3 foot. Yeah, it's 3 foot. So in this case, it's halfway over because that loads uniform. That puts that thing over 1.5. And so 1.5. Now, I'll put my force here. Okay, so if I'm color coding. Hey, wait a minute. Oh, there we go. Okay, so if I'm color coding, let's see. I'll use that one. Okay, so now I've got one. This is the load that I think he's mostly interested in, so I'll call it the C. Or how about maybe force at C? So it's going this way, or the opposite of plus, FC, times the distance from here to here became 4. So I take back what I said. I said that the 4 never comes into it, but it does. But I forgot one thing. And I think, okay, he has told us, this is very annoying. The gate weighs 500 pounds. And its center of gravity is 1 foot to the left of AC. And 2 foot above BC. So it's like right here. Well, as far as the moments go, the force itself goes like this. So I really only care about the 1 foot. And so I really need to go put that back in there, because I've been remiss on doing that. So that's the force I didn't want to do, but here, I'll do it like here, green. There you go. So it's sitting here, and it's 500 pounds, and it's a foot over. And technically, it's going around this way. So that's a positive. So plus 1 moment arm and 500. Wasn't it 500? I think it was 500. So now all you got to do is work out all this junk. So you can see why Fluid Statics Chapter 2, the word statics is in it. So the force of the C is equal to, I'll take that, move that over here, 499, 25, that was times 2.5 for the moment arm, plus, okay, so 250, 25, and a 10 over a 2 times a 3. I got that one from here. And now I'm going to take this one, minus 499, 3 by 5 by 1.5. And then one more, which would be plus 500. And all that divided by that 4 should be the force at C. And I'm actually too tired to type all that even. So, that's a lot to type in. So this is, I mean, essentially, I just took the words and the picture, turned it into a static diagram, used the statics things to turn it into the point loads, and started working with the point loads, and that's it. So from about right here over, well, no, I guess technically this is a pure statics problem, and I guess that's a pure static. So everything here is static. So anything that's fluid is really taking this information right there and turning it into that diagram. So there's your fluids. I can't even spell. And from here over is statics. And so that's probably why they call this section fluid statics. So if you love statics, then you'll really like this section. If you don't like statics, then you... Now there are some common mistakes, and what I'll do is try to go through those. And it's so hard to, I mean, either you make it or you make the mistakes or you don't. And I've never really been able to figure out how a person would make the mistake or not make the mistake, but I mean, I guess that's just the way life is. So it appears like I got 4 minutes. I did the word of the day, didn't I? Did I do that? Oh, okay. All right. Yeah, I was just want to make sure I didn't forget that. Okay. I mean, I don't know. I mean, but I couldn't work any of these in 4 minutes. What else could I do back here? I guess. Well, maybe we'll just say I owe you 4 minutes. I don't know. Yeah, let's just say that. I'll owe you 4 minutes. And if I keep talking, I'll owe you 3. So I'm just going to say I owe you 4.